Good afternoon, everyone. My name is Tanapat Bhakyapaibul, and today I'll be presenting Flying Farther, Designing the Next Toy Glider. So since 1926, the Guilo company has been producing these balsa wood toy gliders. They've become very popular over the years, and as a result, they've been distributed all around the world. If you've played with one of these toy glider in the past 10, 20, 30 years, you were probably playing with a Guilo glider. As a result, they've been able to produce approximately 1.4 million gliders a year to the tune of $9 million. So it's a very lucrative industry. However, what we wanted to deal with was these kind of aging designs. So clearly they work for a reason, but we also want to evaluate how they're evaluate the existing gliders, and that will be done through flight testing, which is just hand tosses and recording data. And then based on that, we'll be able to define our goals. And then we'd also like to deal with this question of the positioning of the horizontal stabilizer, which is just the tail that you'll see on a plane like a 787. I'll go into that in a bit more detail later. And then finally, our overall goal is to design an improved aircraft. How can we improve upon the existing design and make it even better? And so based on initial market research, we were able to see that range and endurance were the two most heavily advertised features. Range being how far your airplane can travel, and endurance being how long your airplane stays in the air. So in our initial testing phase, we were able to determine that the Reverso had the highest average mean of 28.6 feet. And however, the Jetfire did have the highest maximum range of approximately 40 feet. In terms of the endurance, the Jetfire also won out. The Jetfire is that plane that you just saw on the first slide, but their mean endurance is approximately 2.0 seconds with a maximum range of 2.7 seconds. And so what we'd like to do is to be able to improve upon these highest average ranges by approximately 1 standard deviation. And this leads to an increase in range of approximately 17%, which is equivalent to a range of approximately 34 feet on average. And we'd also like to be able to increase the endurance to 2.3 seconds. So how do you design a plane? So there are 4 major important forces when it comes to designing a plane. There's lift, thrust, weight, and drag. Lift is the force that keeps you up in the air and allows you to climb even higher. Weight is the counter to that. So weight is just the force of gravity on your aircraft. Thrust is the forward propelling motion, force. That's typically provided by engines, but because a glider is hand operated, you won't have that force come into play much. And then finally, we have drag. Drag is a really important factor in that it's the force due to air resistance, and it counteracts your forward motion. So the more that you can reduce drag, the farther you can go. So how do you go about choosing all of these things? So the first factor that really impacts drag, for example, is the aspect ratio. So that's kind of just like the aspect ratio on your screen. In this case, it applies to the wing. So it's the ratio of the length of the wing to its width. And by having a higher aspect ratio, that is, if you have something longer and narrower, you'll be able to reduce the drag because you give it less room with which to interact with like frictional forces due to the airflow. Next up, we have the angle of attack. The angle of attack is basically just the angle of the wing or the tail, for example, any horizontal surface made with the incoming airflow. And typically, if you increase the angle of attack, you'll increase the amount of lift that you'll be able to produce, which is good. However, there is a maximum amount of lift that you can produce. And when you get to this amount, what immediately happens afterwards is you experience a sharp drop in lift. And that causes stall. So in terms of stall, just imagine throwing out a sheet of paper and it kind of just like flops around and falls to the ground. That's basically what happens to actual airplanes if you hit this condition. So we don't want that. So how can you prevent that? So there are 2 concepts necessary to this. It's known as the center of lift and the center of gravity. The center of lift is where all of your lifting force is focused. So that's just typically defined as the middle of the wing. And then your center of gravity is is basically where all of your mass is concentrated on the airplane. So by moving your center of gravity in front of your center of lift, you'll be able to stabilize the plane in the case of stall and prevent it from ever happening. And then finally, in airplane design, I'll explain more about this later, but wing loading is a very important concept. It's just the ratio of the weight of the airplane to the unit area of the airplane's wing. So next up, we kind of had to figure out what we had to design. So first you have the wing, obviously, and all of these gliders, they're all flat plates. Then we have the fuselage, which is the main body of the airplane. Then we have the vertical stabilizer. This is the part perpendicular to any horizontal surfaces on your plane. So it's like just the fin for your basic 787 or 777s. And then next up is that important decision of the horizontal stabilizer or the canard. A canard is basically the same as a horizontal stabilizer, which is just the tail, but instead of having it in the back, you can move it to the forward. Now, theoretically, having a canard is more beneficial in that it can produce more lift, allowing you to go even further. But based on our initial testing, we weren't able to really see a difference between the Reverso and the Jetfire models, and so we wanted to explore that more deeply. And finally, we have the ballast. The ballast is the piece that you just move to the front of the plane in order to shift the center of gravity. So after we had all of our design components, there's a lot of decisions to be made, so we came up with a scoring system. So for every single design option, we kind of ranked it based on which one would cost the least, which one would be safest, which one would be more durable. And just to give some perspective, the lower scores tended to be around 60, but these were some of the higher scoring designs of 72, for example. And so this is the aft horizontal stabilizer configuration. This is similar to the Jetfire design, and it looks like this. And so this model prioritizes range. It uses a 3-ply fuselage to improve upon the durability of the aircraft, whereas Guilo just uses the 1 sheet of plywood. And then we have the clip at the front, that's to shift your center of gravity. And then we have the wing pushed all the way forward, and we have the conventional tail. So then we came up with another configuration to test the difference between a horizontal stabilizer and a canard. And this is our canard configuration. As you can see, it's using the same fuselage, except the wing is pushed back. Because most of the mass is now shifted forward, you can shift the center of gravity back a little bit to create that balance that we need. And so that's why the clip is in the middle instead. And as you can see, there's no horizontal stabilizer here. It uses the canard instead. So the first plot you see on the left, designated design point jet configuration. This is where wing loading comes in. So the lower your wing loading, the further away you are from those vertical lines you see. Those vertical lines basically represent the points at which you'll experience stall. So that's, again, when you fall out of the sky. So you want to be as far away from that as possible. However, if you notice, there's drag at the far left. So the lower you are, the higher the drag tends to be. And so you kind of have to find the perfect balance. So in terms of our mass estimates, you can see that our aircraft is heavier, but that's simply because we're using more wood than the Guilo. And if you look at the chart at the bottom, we just have the fact that these are represented as percentages of the whole length of the fuselage. And as you can see, the center of gravity is in front of the center of lift in both cases. So then we tested them out. So the first 2 bars labeled aft horizontal stabilizer 1, aft horizontal stabilizer 2, in terms of the mean range, we were able to significantly improve upon our competitors. They went about 360 inches as opposed to the Canard design, for example, the other design that we built. And so right off the bat, we were able to eliminate that as one of our design choices. However, we noticed that our endurance wasn't as great as Guilo's. In fact, we were approximately half of the endurance of the competitor models. So we went back to the drawing board a little bit, and what we found was that, so I've been telling you this entire time that we want to stay away from stall, but what Guilo does is actually they get very close to stall so that what happens is instead of having a projectile motion, you kind of go down in kind of a staircase trajectory, which lengthens your time in the air. And just by making a simple adjustment, we were able to nearly double our endurance, and this was significantly better than our previous designs, and kind of landed us right in the range of the existing Guilo designs. So in conclusion, we found that the aft horizontal stabilizer worked the best. This is just our actual design that we came up with and built. And in terms of our goals, we were able to get a 20% increase. However, with regard to endurance, we kind of matched the existing gliders. And so for future improvements, we'd kind of like to revisit that Canard design because in theory, it should be better. But for some reason, both the existing designs and our own design didn't seem to show that. And we think that could be due to a factor of interference, for example. So because the Canard is out in front, it's kind of interrupting the airflow to the wing. And so as a result, that could be causing more drag and causing it to fall. And finally, we'd like to investigate the angles of attack a little bit more, because by changing the angle of attack of the tail, we were able to double the time of the aircraft in the air. Yes. So I'd like to thank my team members, Katie Williams and Daniel Su, and also my principal investigator, Professor James Geiger of the Mechanical Engineering Department. Thank you. Questions? Yes, this is just a test flight. Sam?
So when you were testing, did you put any metrics on like how you threw it so that you had kind of a constant?
So actually, instead of having a constant velocity, what we wanted was a wide range of velocities. So we actually had 3 testers. That's just because in reality, they'll be thrown by people with, like some kids will just whip it down like a hallway, and other people will like just gracefully toss it and hope that it goes as far as possible. So we actually had 3 testers, myself and my 2 team members, and that kind of added, from that we were able to determine a range of reasonable velocities to test for. And yes. Sean?
Are you planning to sell or commercialize this design?
It would be very interesting to see that. However, our manufacturing costs are a little high right now, so if we were to produce it, we'd like to keep that, reduce that as much as possible. But yes, their gliders still glide really nicely in terms of that staircasing effect that I talked about. And so if we wanted to sell it, we definitely want to investigate that first. Abby?
So you had said that the Canard might be causing air to be interfered with, and that could cause drag on the wing. Mm-hmm. Is the Canard itself also subject to drag, and would that be a factor?
Yes. Yes, so one way that you can improve the Canard is to do the same thing to the Canard that you did to the wing, which is making it longer and narrower. But the issue with that is now you have a lot of mass out front, and so having too much mass out in front can also destabilize your plane and cause it to just crash instead. Austin?
How does your design compare in terms of size to the Guilo ones?
So typically, when you increase the aspect ratio, you're increasing the size of the wing. So our wing is larger, but actually in terms of the other aspects, our fuselage is the exact same size as our competitor, and so it's not too unwieldy. Okay.